So, hello everyone, we are back. So, what we are discussing is plasma diagnosis lag mirror probe technique. Now, here what we are doing basically there is a research tube within which we have established the plasma discharge and we have inserted a probe, and what we are doing we are just biasing it. That is a very simple scheme. Okay. So, how we are biasing? We are biasing using this controlling this source. So, some current is coming and we are measuring that maybe using oscilloscope or by some other means, and this circuit is basically continue to maintain the discharge. Okay. So, that is what is the basic configuration, and as I told you that when you are going to uh, bias the probe at negative potential. So, then because of the negative region, electrons are not allowed to move over there. So, what you are getting a current due to the ions, and we told that it is a space charge limited current, space charge limited by the ions, and this current what you are seeing here is corresponds to that. Then as you are decreasing the your negative bias, then it is gradually some of the electrons are coming and contributing because they are highly energetic. Even if you try to resist them, they will not stop there, they will try to reach there to the electrode. And then a time is coming when the ion contribution and the electron contribution are exactly cancelling each other. So the your probe current is becoming zero over here, and then when you are increasing the potential to positive region, when it is bit positive, then the probe current starts increasing exponentially, and after a certain time when it is sufficiently positive, then what you are seeing that the current saturates, and this is the electron saturation current. So, it is we are discussing the region when it is very negative, then less negative, then it is slightly positive and very positive. So, the probe current goes like this. Of course, this the type of current density variation that I have shown, it is for a specific type of probe, rather it is for planar probe. If you are using some spherical probe or a cylindrical probe, then the current density variation mostly will be like this, but at this age actually you may see a different kind of variation, and you note the different zones, that this is the ion saturation current, this is the zone where potential where you are getting the probe current 0, and this part contains very useful information as we will be explaining in the later part of this class. And then this is the knee, and this gives you the plasma potential, and this is the your electron saturation current. So, we will be noting each of them and we will be trying to find out the plasma parameters like say temperature, number density and all this. So, when it is less negative bias, that is when we are close to 0, but in this zone only. So, then one goes to transition region wherein the probe current varies very rapidly with increasing voltage in positive direction. As the probe potential approaches the plasma potential, part of the electrons diffusing across the seed edge contributes to the probe current. The number of electrons diffusing and collected by the probe depends on the density of the species, average energy, and also the voltage difference between the probe and the plasma, in addition to dependence on the probe geometry. Okay. So, current varies almost linearly with applied voltage. Now, a potential point is reached where the current becomes 0. So, the point that I have shown you, that time actually what is happening, the your electron current and the ion current, they are cancelling each other. So, in general the probe current, when you are having less negative bias, then the current varies as Jp is equal to Je exponential of E phi minus phi 0 by Kt minus Ji. So, this is the region when your probe current shows this kind of variation. So, this is basically the region you will be getting here. So in this region, the current that will be contributed will be like this: Jp is equal to Je exponential E phi minus phi 0 by kte minus Ji. So what you are seeing that in this region, the probe current contains information about the electron temperature, and of course you need to know the phi which you have applied, and then Je you need to know, and this Ji, this is the your ion current. Okay, so this electron current minus ion current, that is basically the probe current. So here J is the random current density. So when you have applied the zero bias, the probe is at same potential as the plasma. There is no electric field at the point surrounding the probe. The collection of particles by the probe is purely by migration of species due to their thermal velocities. Since the electrons are moving much faster than the ions due to smaller mass, so current is more due to electrons, and probe current is Je minus Ji. Now here I should warn you that there are different sources of error. This is because the change in electron emission function of the material of the probe with bias. So that may cause some source, because you are doing business with the electron dynamics, electrons movement, and thermal electrons and secondary electrons, and electrons due to ion and photon bombardment. So that may cause some electrons which are contributed and which goes unaccounted in the current that you are measuring. So that may introduce some source of error. Then the effect of magnetic field on the electron dynamics, because whenever there is an electric field, that will make the electrons to gyrate, and sometimes it may happen that the radius of gyration is smaller than the diameter of your probe. So your whole probe is not collecting the electrons, so they are only part of that is collecting the electrons. So it depends on the kind of situation that has arrived, but these are the influencing agents. So what are they? They are the magnetic field, the secondary electrons, emissions due to ion and photon bombardment, then the change in electron emission function as a function of the bias, so of the probe material actually. So all this can contribute some error in the measurement. So we should be aware of those effects when we are trying to critically evaluate the curves of current against the applied bias. Now when we have a positive bias, so more positive voltage when we are applying, the ions are repelled, resulting in the current mainly due to electrons increasing their acceleration towards the probe actually. So you have applied a positive bias, so electrons are getting accelerated towards the probe, so and ions are gradually getting repelled. The positive voltage introduce an electron space charge sheath that is possible between the plasma and the probe sheath. Okay, so there is a space charge accumulation of electrons that may happen, and for voltage above the plasma potential, all positive ions are repelled, resulting in a saturated electron current. So what the part that we are seeing over here, so this part, so this is the electron saturation current. Now the electron current becomes saturated as the area of the sheath is relatively constant when the probe voltage is increased. So Jp is equal to Je plus Ji. So here for very high positive potential, sudden increase in the current is observed due to ionizing collision by the electrons. Now here what I am showing you, the similar curve, what I have just shown you the curve, that is due to the planar probe. When you are using a cylindrical probe, so the current may vary with the applied bias like this, and spherical probe this may go like this. So what you are having here, this is the your ion saturation current zone, so this is Ji. This gives you the your floating potential of the plasma, and then this part is the linear part where you have seen the current equation that it follows, and then this forms the your electron saturation current. Okay, this is the ion saturation current. Now the zone where the knee occurs, that gives you the plasma potential. So it is very easy to find the knee point of the current voltage curve, and here what you are seeing this point, that corresponding voltage what you are applying over here, so that gives you the plasma potential phi 0. Now this part is electron saturation current and this is the exponential zone. We will be using this linear part, mostly linear part of this zone, and that we will be using for finding the electron number density. Okay, so this exponential basically this is the exponential zone, but this part almost looks like linear, and after that this is another linear zone. This is almost a saturation zone, slightly increased because the increase of the this space charge zone. So the slight increase in the current is there, but this is mostly a saturation electron saturation current zone. So how we will use this information to find out the electron number density and electron temperature, that we will be now discussing. Okay. Now when the bias potential is very high negative, okay, large negative potential, then you have seen that the characteristic is giving a ion saturation current. So we can note that current, and so we note the probe current as Ji. So we note the value of Ji there. Now what is the Ji? So this is the Ji as I am marked over here. Okay. Now when your potential is very large, positive, then the plateau of the characteristics gives the random current J is equal to Jp minus Ji, and it is you note the value of Je. So whatever probe current you are getting, so that is basically the ion electron saturation current. So you know the value of Je. Now for moderate positive potential, you are getting the linear region of the characteristic, where you are getting basically this is an exponential curve. So Jp is equal to Je exponential of E phi minus phi naught by kte minus Ji. So what you need to do now, you plot Jp plus Ji, take this Ji left side and take a log of that. Then what you are getting on the right hand side, this becomes a bare term. So E phi minus phi 0 by kte. So if you plot this Jp as a function of phi, the applied bias, then what you are getting a linear curve. And what is the slope of that? This is E by kte. Okay. So slope of that linear curve is, this is a semi-log plot, because log in one side and another side is just plotting as a function of phi, and the slope of that is E by kte. So slope we write it as G, that is E by kte. So Te you can just determine like E by Gk. So it is so easy. So you just make a plot, you sweep your voltage, get that semi-log linear plot, find out the slope of that, and that is equal to E by kte, and from that you determine the electron temperature as E by Gk. Now you know that from the kinetic theory, if you have a gas, then number of particles which are moving towards the wall, one wall, suppose you have a rectangular chamber and you have 6 walls, top, bottom, left, right and front, back. So there are 6 walls, and towards one wall, if you want to find out the flux, you know that the standard formula is nc bar by 4, where c bar is the average velocity. So it is n v average velocity divided by 4. Now what is the average velocity from kinetic theory again? You know that it is 8 kT by m pi square root. So it is n by 4, 8 kT by m pi, and if you take 4 inside, then n kT by 2 pi m. So that is the flux. Then what is the current when you multiply this flux with the charge? So when you multiply this by electronic charge, so it becomes Ne kT by m 2 pi m square root. So what you are interested in? You are interested in n. So you just take this n and divide this j divided by e root kT by 2 pi m like this. So Ne you get as j by e root square root of kT by 2 pi me. So you are now very much clear that the characteristic once you obtain just by sweeping the voltage from negative to positive, and you plot make a semi-log plot of that exponential part, exponential region that you get in your curve, then from the slope you are able to find out the temperature of the electrons, and from the your again from the curve, if you know the electron saturation current Je, then from that you are able to find out the electron number density just using this formula. So you are now clear that how from the Langmuir probe setup you can determine the electron number density and electron temperature very easily by sweeping the voltage from a negative to positive value and noting the current that you are getting through the probe. So in summary, we have ion saturation region when V is much less than plasma potential. The probe is highly negative, it repels most of the electrons and collects mainly positive ions. The current saturates at a negative value, that is giving you the ion saturation current. Then second, we have electron retardation region when V less than the plasma potential but not too negative. Then the probe starts attracting some electrons and current increases exponentially with applied voltage. Then third comes the electron saturation region when the applied bias is much greater than the plasma potential. The probe is positive enough to repel ions and attract electrons. The current saturates at a positive value, the electron saturation current we obtain. And using this formula, we can easily find out the electron number density and electron temperature from the curve parameters that we have just obtained. So we obtain the electron temperature derived from the slope of the exponential region, and electron density calculated from the electron saturation current or from ion saturation current using known theory like Bohm-Schmidt. This is another thing. So we have already studied the Bohm-Schmidt criteria. Now plasma potential can be found where the first derivative of the IV curve is maximum or where electron and ion currents balance. Okay. Now we will do one tutorial in the tutorial class, and we will note the your probe current and probe potential, and we will try to find out what is the electron number density that you can calculate from there. So this we reserve for our tutorial class about the finding the actual number density and electron temperature when we are given a chart of potential and the measured probe current. So we will do that in our tutorial. So now I will switch to plasma applications part. Okay. Now you know that plasma application has wide variety of areas. So thermal and cold plasma application includes this noble material synthesis, electronics industries, they are for plasma etching. It is all IC industries are using this cold plasma, basically glow discharge mode. And then that noble material synthesis, so where we are synthesizing variety of noble materials. So starting from these nanoparticles to graphene-like structures to 2D material to quantum dots, all this noble material can be synthesized using this plasma as a very a fantastic tool. Now, apart from these novel areas which are emerging nowadays, electronic industries are using this cold plasma for quite some time in the semiconductor industries. Now, you know that PVD, CVD are regularly used for thin film coating. So, where the thickness of the coating is less than a micron. Okay. And when you are willing to have a coating of say higher thickness, maybe say 200, 300 micron or maybe 600 micron kind of thing, then this PVD, CVD are not suitable because they are only for thin film applications. There you need to go for this atmospheric pressure plasma spray coating. So, where you can develop say 600 micron thickness of coating in just a minute. Okay. So, these coating applications are having widespread applications in many areas and very novel applications where you need suppose a coating which will be able to withstand the environment that is very harsh in nature, and it will protect the material. Not only it will protect, it will may act as a thermal barrier coating or it may act as an environmental barrier coating at that point, or it may act as a corrosion resistance coating. So, this APS coating are very useful in many important industries, like there are certain very reactive material like say molten uranium. It can react with any material, any metal, but you require metal for containing the substance. So, but you cannot put your molten uranium say in a pot because it will react with that. Then what you do? You coat that crucible with your some material like say yttrium oxide. Basically the rare earth, they can protect the material from highly reactive substances like molten uranium. So, you can coat that crucible using say yttrium oxide or say some rare earth oxide to protect that material of the container from reacting with the molten uranium. So, there are certain applications where this novel nature of this kind of coating are extremely useful. Another application may be the turbine blade, because they are rotating at very high speed and they are meeting many of the times very corrosive environment. A protective coating using say APS of several hundred microns can protect the turbine blades to a great extent and increase their life amazingly. Now, this plasma cutting and welding industries, they are very well known and billion-dollar industries. Almost most of the very thick metal cutting industries are using plasma as a basic tool. They can be programmed using robotics and they can do a profile cutting very neatly and in very short time and very cost effective manner. And the welding arcs, almost most of the stainless steel industries are using this welding arcs. They are called TIG welding, tungsten inert gas welding. So, the arc that is being generated there, they are causing the welding, and similar arc in case of cutting, they are doing the cutting job of thick metal plates. Now, the area of plasma metallurgy, basically using plasma in a very extensive way. The melting industry, steel melting. So, where we are using thick graphite rods and making a transfer arc between the metal and the electrode, And that way what it is doing, it is transferring almost more than 90% of the electrical energy into the metal which is going to be melt. So that way it is a very effective way of melting metals in arc furnaces. So this is one of the application. The other application is that because plasma is having very high energy, using appropriate plasma gas, what we can do actually, we can generate a reactive environment for a specific processing purpose, so material processing purpose, so which will do certain reaction and extract the desired attributes that we want to have. For example, suppose in case of sludge treatment, you know that sludge is going to the drain, and if you use those sludge, there are various different types of sludge which are coming from the industries as well as from the municipalities. So especially the chemical industry sludge, where the sludge contains many useful material together with the organic substances. So the moment you apply your plasma into that, the most of the volatile organic components just evaporates away, and what you are left with is the organic inorganic component. Now, depending on the kind of plasma you are using, the inorganic component can react with that and form some other compound which can be separated easily from each other. So that way the plasma acts as a wonderful tool in case of plasma metallurgy. So you starting from material refinement to plasma cutting to plasma coating to novel material synthesis to electronic industries, they are all working very fantastic. Now, recent application of this thermal and cold plasma includes the area of agriculture, medicine, waste management and material qualification under extreme conditions. So this right side one, they are basically some of the most recent application of this thermal and cold plasma. Of course, novel material synthesis, they are expanding like anything nowadays, because plasma is acting as a magical tool for getting newer and newer types of new materials. Now, in the rest part of this course, what I will tell the applications, specifically I will emphasize on this waste management, agriculture, medicine and this material testing under extreme conditions. These are required because rest of the things, electronic industries, then plasma nanosynthesis, of course I will tell something on that, and plasma cutting and welding and plasma CVD, they are widely available in literature. But you know, this plasma nanosynthesis, this agriculture, medicine, waste management and material qualification under extreme conditions, they are some of the areas which are usually you can say less discussed. So I will emphasize on those part because rest of the other parts are easily available in literature. So I stop here, and from the next class onward I will start the application areas of thermal and cold plasma. Okay. So see you in the next class.